Hello students, myself Dr. Richa Srivastava, and in this video lecture I am going to discuss active filters, that is low pass and high pass. Now first of all, what is a filter? Filter is a electronic circuit that performs frequency selection function. It means it passes certain range of frequencies which lies within the specified range, and it stops certain range of frequency that falls outside this range. It means it has one pass band and another is the stop band for the filter. Now depending upon the pass band and stop band, there are different types of filter. These filters, they are low pass filter, high pass filter, band pass filter and band stop filter. Here we can see the frequency response of a various filter. This is the ideal frequency response of various filter. Here first is the low pass filter. The x axis is the frequency axis, that is omega axis, and this is the gain. And here we can see it has a pass band up to omega p, that is the cutoff frequency of the filter, and this is the stop band. After omega p, it is the stop band. It means the filter, it will pass the frequencies from 0 to omega p, and after that it will block these frequency. So this is the ideal characteristics of the low pass filter. And then it is a frequency response of a high pass filter. Here from 0 to omega p, it is a stop band, means these frequencies it will not be passed by the filter, and after omega p, the filter it will pass the frequency. This is known as the pass band of the filter. Then is the band pass filter. Band pass filter, it means it passes a band of frequencies, and this frequency it ranges from omega p1 to omega p2. It means omega p2 minus omega p1, it is a range of frequency that will be passed by the band pass filter, and below omega p1 it will be lower stop band, and above omega p2 it will be upper stop band, and in between it will be the pass band. So this is the frequency response of the band pass filter. Another is the band stop filter. Band stop filter means it stops the particular range of frequencies starting from omega s1 and omega s2, means this difference of frequency, this range of frequency, it will not be passed by the filter, it will be stopped by the filter, and below this frequency the frequencies will be passed, and above also this frequency will be passed. So this is the lower pass band and this is the upper pass band for the band stop filter. So this is the ideal characteristics of all the filters that we have, and in this way we can analyze how the filter it passes the range of frequency and stop the particular range of frequency. Now before studying any particular type of filter, the filter transfer function, this is the general expression. It is having certain zeros and certain poles, Z1, Z2, Zm. It defines the zeros of the system or transmission zeros, and denominator P1, P2, Pn, they are the transfer function poles, or it is also known as the natural mode also. So each transmission zero or pole, it can be either a real or a complex number, and if it is a complex number, then it must have its conjugate pair. It means, let's say if one of the 0 is minus 1 plus j2, then another 0 it will be minus 1 minus j2. So this is the general expression, and with this general expression we can find out the expression for low pass and high pass filter function. Now first of all, coming to the low pass filter, first order low pass filter, how we will implement it using operational amplifier. It will consist of a op-amp. This is the operational amplifier, and at the inverting terminal we will have the feedback circuit with R1 and R2. This is the feedback part. this is the feedback, this is the output voltage, R1 resistance, R2 resistance, it will be at ground, and at positive we will have the combination of R and C. So, we will have a resistor and a capacitor over here. This is R and this is C, and here we will apply the input signal. This is the input of the filter and this is the output, and here we have applied R and C. So, this is the circuit diagram for first order low pass filter. Now, to analyze this circuit, what is the first step? We will apply the concept of virtual short because it is having negative feedback. So, virtual short will be applied, means if this is the node A and this is the node B, then VA voltage it will be equal to VB voltage. So, to find out the VA voltage, we will apply in this loop, we will apply the voltage divider rule. First of all, VA voltage in terms of V in voltage, it will be V in multiplied by the impedance XC divided by XC plus R. Now, impedance XC it can be written as V in into 1 upon SC divided by 1 upon SC plus R. So, VA voltage it will be V in divided by, here SC will be cancelled out, then we will get RSC plus 1. So, this is the first equation, we have calculated VA voltage. Now, VA voltage we have calculated, VA will be equal to VB, or we can analyze this as a non-inverting amplifier whose input is VA. So, for non-inverting amplifier, the gain, that is VO upon VA, it is 1 plus R2 by R1. Now, in this equation we will put the value of VA from equation 1. So, VO upon VA is V in divided by RSC plus 1, it will be 1 plus R2 by R1. Now, from this VO upon V in, it will be 1 plus R2 by R1 into 1 upon RSC plus 1. So, the final transfer function of this filter VO upon V in is given by this expression, and this is the transfer function of the filter. So, HS it will be 1 plus R2 by R1 divided by RSC plus 1. This is the final expression for the low pass filter. Now, if we analyze this expression at S is equal to 0, the gain of the filter it is given by 1 plus R2 by R1. This is the DC gain for the filter, and the function it is having single pole. The pole it is given by, if we put denominator as 0, so the pole of the filter it is given by minus 1 upon RC. This is the pole frequency of the filter. So, if we draw the graph for this filter, this is the x axis, that is omega, and this is the gain of the filter. So, At s is equal to 0, the gain is 1 plus R2 by R1, means it will start from this point and this gain is 1 plus R2 by R1. And with frequency, as we see, as s increases or frequency increases, the gain it will be reduced, and the frequency at which the gain, it is 1 by root 2 time, it is the cutoff frequency, and here we will mark this as omega c. It is equal to minus 1 by RC. So, from the expression it is clear that this is the function for low pass filter. From 0 to omega c, the frequencies will be passed. This is the pass band of the filter, and after omega c, the gain it reduces, means the filter it will start blocking these frequency. So, this is the expression for low pass filter. Now, next we will discuss first order high pass filter. What is the difference between the circuit diagram for first order high pass filter? It is having a op amp. Again, the negative terminal, it is having resistance R1 and resistance R2. This is the output voltage, and this will be at ground, and at the non-inverting terminal we are having, at the input side we are having the capacitor and resistance at the ground. This is C R, and here we apply the V in. So, the basic structure is same, but here R is replaced by C and here C is replaced by R, if we compare this circuit with the low pass filter. Now, coming to the analysis we will start by calculating this voltage, this node voltage A, that is VA. So, VA voltage, it will be equal to V in voltage multiplied by the resistance across which we want to calculate the voltage, divided by R plus impedance of the capacitor. It can be written as V in multiplied by R divided by R plus 1 upon SC. So, VA it will be V in into R divided by RSC plus 1, and here also we will get RSC. Now, once we have calculated VA voltage, here VA voltage, again this will be a non-inverting amplifier with input as VA. So, the second step, VO upon VA, it is given by 1 plus R2 by R1, and from this expression put the value of VA. So, it will be VO divided by V in into RSC divided by RSC plus 1. So, it will be equal to 1 plus R2 by R1, and from this VO upon V in, it will be 1 plus R2 by R1 into RSC divided by RSC plus 1. This is the expression for the transfer function of high pass filter. Now, if we see over here, if we put S is equal to 0, means for S is equal to 0, the H0 or gain it will be equal to 0, means the transfer function curve it will start from the origin only, that we will see also how it will start from origin, and at S tending towards infinity, if we put S tending towards infinity in this, then the H tending towards infinity, it will be equal to 1 plus R2 by R1. So if we plot the graph for this, this is the y-axis and this is the x-axis, that is omega axis, and this is hs. So at 0, s is equal to 0, the transfer function is 0, so it will start from this, and after that it will be constant, and this constant gain is given by 1 plus R2 by R1. And the cutoff frequency of this filter, omega c, it is given by minus 1 by RC. It is obtained by putting the denominator to 0. So, omega c will be minus 1 upon RC. So, this is the, again here this is the pass band. After omega c, it is the pass band of high pass filter, and below omega c it is the stop band. So, in this way we have calculated the transfer function and analyzed the waveform, or we can say the graph between frequency and gain, how the pass band and stop band is obtained in low pass filter and high pass filter. So, in this video lecture we have discussed the implementation of a low pass and high pass filter using operational amplifier, and we have discussed its characteristics also, how the stop band and pass band will be implemented in these filters. Thank you.